questions from last time? So I introduced the Fourier transform on R. Okay, by the way, the conventions are varying in different books and it can be quite confusing. One must always figure out when looking at it, because here we define the Fourier transform of an L1 function as f against E lambda bar, but E lambda bar for us is e to the 2 pi I lambda x. Okay, so there is a 2 pi. So sometimes Fourier transform is defined without the 2 pi there. It is e to the minus I lambda x. People also divide this whole integral by square root of 2 pi. There are many things one can do, and somewhere or the other you have to be careful about the conventions when you try to transfer the formulas. Okay. Anyway, so we'll stick to this, and for f in L1 or measures, we can define the Fourier transform, and then we were seeing a few basic things. So such as that the Fourier transforms of measures are going to be bounded continuous functions always, and if it's L1 function, then it also vanishes at infinity. Okay, so for both measures and L1 functions, the Fourier transform is a bounded continuous function on the real line, and for L1 functions, it vanishes at plus minus infinity. So that is the Riemann-Lebesgue lemma, very useful. So that means that if absolutely continuous measures, then mu hat of lambda must go to 0. So sort of converse type of statement is that if mu hat lambda goes to 0, that's not enough to say mu is absolutely continuous. That is, it has a density. But if mu hat is L1, then it is true, and you can recover it as the Fourier transform of the Fourier transform evaluated at minus x, and you have to divide by 2 pi. So this is why I said that the convention is important. So depending on whether or not you put where you put the 2 pi's, so you may or may not have this factor. Actually, so why do I get this factor? Do I have 2 pi or not here? So yeah, now I'm actually confused whether I should have a 2 pi or not here. Yeah, I'm going to make it completely confusing, because now I'm totally confused whether this notation choice was a wise one. I usually do with I to the minus I lambda x, and that I often at least remember the formulas. But now, yeah, where did the 2 pi come from? Okay, let us look at, so this actually inversion comes from here. So let f be in L1 and in, sorry, not there. Suppose f is a, right, where do I get this from? If mu is in M of R, then I got this. Why do I get this? So I said proof similar to circle case. Now, there may or may not be 1 over 2 pi factor. One should be a little careful. It's best to check it in a simple case. So let's take Gaussian. Okay, so did I give examples at all? Yeah. So when mu is Gaussian, mu hat of lambda is e to the minus lambda square by 2, right? So if I take mu hat of lambda, so let me just check whether or not there should be the 2 pi factor. Here, for this particular example, mu hat of minus x, what is it going to be? See, mu hat is actually Gaussian, except that the square root 2 pi factor is not there. So I can write 2 pi times mu hat over 2 pi square root 2 pi, and then take the hat at minus x, which will give me square root 2 pi. Now it is exactly the same as the original Gaussian density, which will give me e to the minus of minus x square by 2. Okay. So this is what mu hat of minus x will give me square root 2 pi times e to the minus x square by 2. Okay, so there should be a 1 over 2 pi factor. To get back the density, you need 1 over square root 2 pi, not square root 2 pi. So you should divide by 2 pi. Okay, so by looking at example, it is correct. This seems to be correct. Okay, so I also mentioned how this inversion formula comes. There is a more general inversion formula. Even without assuming mu hat is in L1, you can recover a measure from its Fourier transform by a limiting operation. You just integrate mu hat against this thing and let L go to infinity. You get, so this is similar to the Fourier inversion formula we had in the circle case. Then I was talking about the smoothness versus this of the Fourier transform. So let me see what all I have said about it. If f is smooth, that is f is in L1 intersection C1, then f dash is also an L1 function, and we are assuming f dash is an L1 function, then f dash hat is 2 pi lambda. So f hat will decay. So smoothness of f implies decay of f hat. This we said last time. F is ck, then fk is L1, and fk. So therefore f hat lambda will decay faster than 1 over mod lambda to the power k. Okay, strictly faster than that. The other way, if f hat decays fast, then f is smooth. That is something that I mentioned here, and I gave it as exercise. So if you assume f hat times, so f hat is in L1, then fx is, so first one is when k is 0. If just f hat is in L1, this is the inversion formula. Okay, exactly like mu hat in L1, that's case. So you get fx back as f hat of minus x, which also shows that if f hat is L1, then f has a continuous version actually. Because Fourier transforms are going to be continuous, f hat is continuous. So you can, this almost sure equality means that even if originally you started with an L1 function, if its Fourier transform is L1, then f is actually, you can just change the definition on a zero measure sets to make it continuous. So, and you get this. And then if you want to go further, so next suppose f hat lambda times mod lambda is integrable, then you can just differentiate under the integration here and show that f dash will be recovered from f hat like this, and so on. And then you can continue. Okay, so this is the point that decay of f hat implies smoothness of f. Okay, any questions so far? So let me say something which we will not be using much here, but it is something that is good to know. Quite often, I mean, in analysis, we have seen this. So when you want to work with some L1 functions, LP functions, it's good to have a subclass of nice functions for which you can prove the result first, and then get the result, right? So that, so what is a good class of functions when you work with Fourier transform? I want to mention that. But before that, let me just mention one thing. Srikanth reminded me yesterday. It's a point which is good to know, that so this decay of Fourier transform and smoothness, you will see this in probability actually. So just as a side remark, let me say, if mu is a probability measure on R, then the typically, so what, I mean, if you look at this type of thing that we have written, so what we can see is, okay, so mu hat of, no, let me just write e to the minus, actually I am completely off here. Actually, I made a mess of things. Yeah, so with the 2 pi here, the formulas I wrote for the Gaussian Fourier transform were incorrect actually. There would be an extra 2 pi here. Yeah, so I don't know what I should do now. It's not true that mu hat is this. This is true if I take e to the minus I lambda x. So I am now unsure about a lot of things. What should I do? Yeah, it's a pain now. I should have just stuck to e to the minus I lambda x, which at least I usually remember. This is actually, no, this is also not quite correct, because you will get you will get 2 pi lambda square. So you will get not this, but e to the minus 2 pi lambda squared, which is right.
Yeah, I mean, actually, Manju, if you make the, if you look at e power minus pi x squared, then it is what you have written is correct. Then it's the Fourier transform is the same as itself.
Yeah, that's what I will have to take it. But this 1 by 2 pi factor, what about that? Should it be there or not? I mean, 1 by 2 pi factor in the inversion formula. Yeah, it's a bad choice I made actually. Yeah, I'm thinking whether I should go back and change the definition of Fourier transform.
Yeah, I think if you change that, then I think there will be a 1 by 2 pi factor. you just make it I
Yeah,
lambda
there
x.
will be, but now whether there is or not, I don't know. And various things I wrote will have to change a little bit. Yeah, so what shall I do? Yeah, actually, a lot of things here are, I think, incorrect. So I actually better change it completely. Sorry about this. Now I realize that yeah, it makes a lot of. I was saying that one has to be careful, but I forgot I have to be careful. So let me just quickly redefine. Okay, so sorry about this. We'll change convention. None of the things I said is actually, I mean, incorrect in spirit, but the exact formulas, whatever was written in the previous page, treat everything as suspect because the exact formulas are not going to be correct. So let's define E lambda of x now to be e to the I lambda x. Okay, no 2 pi in the exponent. And for f in L1 of R, define f hat of lambda to be fx e to the minus I lambda x dx. Okay, so let me define it like this. So various things are which I said are actually going to be remain. So and for mu in M of R, which means finite measures, mu hat of lambda is going to be defined with e to the minus I lambda x d mu of x. Okay. So many things that I have said are true, and I will not write all of them. So for example, mu hat, f hat are bounded continuous. And bounded in fact by or less than equal to mu of R. Similarly, f hat is bounded by f L1. So those things are true, and for f in L1 of R implies f hat of lambda goes to 0 as lambda goes to plus minus infinity. All these are true, except that where I wrote there were factors of 2 pi, you will not have them. Okay, so that is also there. Okay, what were the other things? The inversion formula will hold in the form I wrote. I will write only the case when, so if mu hat is in L1, then mu has density. It is actually a bounded continuous density, in fact. Which is given by mu hat of minus x divided by 2 pi. Okay, by the way, now it is true what I had said earlier, but the examples that I gave, if mu is the Gaussian measure, then mu hat of lambda is e to the minus lambda square by 2. That is true. And for uniform on minus 1, 1, mu hat of lambda, last time I had sine 2 pi x over 2 pi x. I think it will just become sine x by x. So I had sine 2 pi lambda x, sine 2 pi lambda by 2 pi lambda. The 2 pi won't be there. So it will be just sine lambda by lambda. I think this will be the Fourier transform and so on. Okay. So I will not be repeating everything, but let me write a few things so that these things are in place. So this is true. And similarly, if f is in L1, if f is in L1 and f hat is in L1, then f of x is f hat of minus x over 2 pi. Almost surely. Meaning that you can, of course, this means that you can change f so that it becomes equal to this. Change f in a set of zero measure so that it is this bounded continuous function. So this is true. And let me just say that more general inversion formula exists, which I will not write again, without assuming mu hat is in L1. So the more general in the notes, maybe I will try to write it properly. So this type of formula which I wanted, where was that? This kind of thing, that mu AB plus half of mu at the endpoints is equal to this. You can write such a formula. I think it will be exactly this without the 2 pi's here. There are no 2 pi's in this, e to the I lambda b minus e to the I lambda a over I lambda. But there is a 1 over 2 pi here. I think with that, this is exactly the formula. But I will write it properly in the notes, hopefully, if I manage. Okay, so that is also done. And then what are the other aspects I had covered? So the smoothness and decay. Let me come to that point because that is where I was headed next. So smoothness and decay. Oh, but before that, some simple things actually, some simple transformations. If you take, if f is in L1 and you do g is f of x minus a, if you translate, then of course g is also in L1. What will be g hat of lambda? It will be g hat of lambda is you will just integrate e to the minus I lambda x into g of x, which is f of x minus a dx. So if you change that x minus a to x, here it will become x plus a. So you will get e to the minus I lambda a f hat of lambda. So if you translate a function, then on the Fourier side, you will just multiply by that corresponding exponential e to the minus I lambda a. Okay, so and if you scale a function, let's use a different f of b times x. Okay, it is more natural to divide by b so that L1 norm remains the same. Okay, actually, it's better to the way of scaling. It is better if I write it as f of x by b. Yeah, then what is the thing I should do to keep the L1 norm the same? G of x dx will be f of x by b dx. So if I have dx by b, that will be better. Sorry. So this is how I should scale, where b is positive. Here a is any real number. B is a positive number. You scale g by like this, and you also do it so that L1 norm remains the same. Then what is g hat of lambda? Well, you will get e to the minus I lambda x f of x by b and dx divided by b. So you just write this as x divided by b times b. So what you see is that if I make variables x by b as y, then you will see that this is same as f hat at b lambda. Okay, so this scales in the other way. So what this is so this is a simple form of uncertainty. Okay. A simple form of Because what is it? If B is large, if B is, so if B is see, this is, what is this? I mean, if, what does this mean? F of x by b, what does that mean? So if f was a probability density, this would be the probability density of b times x. So if b is large, or if b is small, then g is more localized. So what I mean is, suppose f is like this. Then if b is small, then what does g look like? G will look like this. It is b small means that it's normal with variance 1. This is normal with variance small variance. So the density will look very peaked. Okay, so it should be, I should write like this. It goes up and comes down very fast in a shorter interval. But then f hat was the same one, right? Except that the scaling is different. But g hat will be, if you see, it is f hat of b lambda. So that will be kind of spread out. So if you try to make f more peaked, then by changing scaling, then the Fourier transform side, it will scale out. Less localized. So this is also a manifestation, a very simple one of uncertainty principle. That if you scale, if you kind of localize on the one side, you will go on the other side. So both cannot be too localized. So most uncertainty principles are of that form. I mean, qualitatively all uncertainty principles are of that form, that function and Fourier transform cannot both be localized. But you can come up with many different senses in which you can talk about localized, and that leads to different uncertainty principles. So this is something I had not said last time, but this is a simple one. And yet another one, which let me mention, that convolutions also go as before in the circle case. So if mu and nu are in M of R, mu star nu is defined by mu of A minus x d nu of x. And if f and g are in L1 of R, the convolution is defined as f of x minus y g of y dy. Integrals are over the real line. Okay, and these two are consistent definitions in the sense that if mu and nu have densities, mu star nu will have density which is f star g. Okay, so this is that consistent in that sense. Will have density f star g. So in that sense, it is consistent. But the fact is, so this is an exercise I had left in the circle case. You can do the same here. Mu star nu hat is mu hat times nu hat. And same with the L1 functions. F star g hat is f hat times g hat. So this is the this is, by the way, the interpretation is the same as before. If mu and nu are probability distributions, then mu star nu is the distribution of x plus y, where x and y are independent random variables having distributions mu and nu respectively. So this is why this product form, that convolution becomes, convolution is a little complicated. I mean, addition of random variables is a little complicated. We can't easily find the distribution explicitly. But on the Fourier side, it is simple, that it's a product. This is the reason why Fourier transforms are useful in probability. In basic probability, where we are studying sums of independent random variables, Fourier transforms are extremely useful. If you go to study not independent random variables and so on, then it becomes less and less useful. But the basic theory that we study in probability theory class is for what do sums of random variables behave like. So you prove things like law of large numbers, central limit theorem, and so on. For all those, you can use Fourier techniques to prove such things. Okay, so that is something I had not mentioned again last time. Now let me come to decay versus smoothness. So F is in L1 intersection CK and Fk is in L1 implies f hat of lambda is little o of mod lambda to the minus k as lambda goes to plus minus infinity. I had indicated this last time. Exactly the same proof, except whatever factors of 2 pi were there are not going to be there. Similarly, f hat, if suppose f is L1 function and f hat of lambda times lambda to the k is L1, then that means f hat decays fast. Then f is in ck, and in fact you can write fk of x. You can get it by, see, you have the, basically you have the inversion formula, which is f hat of lambda e to the I lambda x dx over 2 pi. You just differentiate under that k times f hat of lambda I lambda to the power k e to the I lambda x dx over 2 pi. Okay. Yeah, so this type of thing is true, and so in case of, but you can also go the other way because both sides are real line. In circle case, we could talk about smoothness of functions on T and decay on Z. It didn't make sense to talk about decay on the circle group because it's a finite space, compact space, and there is no meaning of smoothness on Z. But here you can also go the other way. You can also do, here it is smoothness of f implies decay of f hat, and decay of f hat implies smoothness of f. So this is related to decay of f hat. But the other way is also true. You can also talk about decay of f and smoothness of f hat. Okay, why? Because exactly the same reason. I mean, because of inversion formula. Suppose suppose f decays fast. Then f hat belongs to ck, and it will be in fact f hat k of lambda. You just write the formula for f hat of lambda like here. F hat of lambda is f of x e to the minus I lambda x dx over dx. There is no 2 pi. You just differentiate it k times, whatever you get. So will be f x into minus I lambda to the power of k e to the minus I lambda x dx. There is no 1 over 2 pi here. And you can also do the same the other way. And suppose f hat is smooth. F hat is in ck intersection L1, let us say. Okay, I mean, if not that, if I want f hat k is in L1. Then exactly like here, except that the assumptions are on f hat, because the relationship between f and f hat both ways is roughly the same, provided you assume the integrability and so on. Okay, and I don't mean just f hat, let's just assume f hat j in L1 for all j less than equal to k. I think here also I should state it that way actually. F hat j in L1 for all j less than equal to k. I think better to state like that, that all those are in L1. So then we will get that F is little o of mod x to the power minus k as x goes to plus minus infinity. Similar thing. Okay. Say I earlier I had just written f k is in L1. That may not be enough. I think you assume all the derivatives are in L1 because I was doing inductively, right? So I think maybe that is the better way to write it. Anyway, so this both ways are true. Smoothness of f, decay of f hat, decay of f, smoothness of f hat are all related. Any questions so far? So I repeated some of what I had done last time, along with two new things, these transformations and convolutions. Okay. Because of this, so what is a good class? A good class of functions to work with. When you're studying, especially when you're studying Fourier transforms, see, the thing is often what do we take? We take step functions or smooth functions or compactly supported smooth functions. Problem is when you go to the other side, those things may break down. For example, compactly supported function like uniform on -1, 1 has density which is half on -1, 1. If you look at its Fourier transform, it is a very nice smooth function. Actually, it is infinitely differentiable. But this one is a discontinuous function. Conversely, this is a compactly supported one. This is not compactly supported. In fact, it decays very slowly. It decays like 1 over lambda. So this type of issue is there. When you properties that you have on this side may not go to that side, because that's exactly the theme we were saying. You may assume smoothness on one side, but then that will give you decay on the other side, but not smoothness. And similarly, if you assume decay on this side, you will get smoothness on the other side, but not the decay. So what is a good class of functions to work with? You assume all those things on one side, then you'll get all those things on the other side. Okay, so that is called a Schwarz class. Is the space of all functions from R to R such that f is, first of all, infinitely differentiable. It should be infinitely smooth. And for all k and L, P, let's say, if you look at kth derivative of x, okay, you take you take any derivative for all k greater than equal to 1, p greater than equal to 1. This statement is even 0. Okay, so let's say k equals 0 means the original function. Okay, and yeah, so let's say for all integers, so the kth derivative of f should decay faster than x to the minus p. So let's say x to the p times this goes to 0 as x goes to plus minus infinity. Okay, so any derivative times any power decays at infinity. So it's a good, so it has to be both smooth and the decay, both have been assumed. Then it is easy to see, not hard, then f hat also is in the Schwarz class actually. Because f decays fast, f hat will be infinitely differentiable. And because f has all this smoothness, f hat derivatives will also have that, I mean, f hat derivatives will decay because, again, I mean, so f hat also, so I will just leave it as either exercise or lookup. We will not be using these functions much. In fact, the Fourier transform is a bijection of S of R with itself. So you can take S of R to S of R. The Fourier transform is a bijection. I had mentioned that so a lot of nice theorems, basic theorems which are nice in Fourier analysis, just identify the range of Fourier transform on some subclass of functions. Now on measures, I will come to it. We know what the range is, but L1 functions we don't know what the range is. But this is a nice class of functions whose range we know exactly. S of r goes to itself, and it's a bijection. So one example, of course, of this is Gaussian. E to the minus x square is such a function. Or even you can take a e to the minus x, okay, times mod x to any power. These are, you have sufficiently fast decay, and okay, I shouldn't write mod x to the power m. That will not be smooth, right? So that is why. Let's just take an even power for simplicity. X to the power 2m times e power minus x. So this, you see, it is infinitely smooth, that is clear, but however many times you differentiate, there will always be an e to the minus x factor, which will make sure that even though your powers will be big, but it doesn't matter, it will kill all that. So these are Schwarz class functions. So they are very nice. So, but I won't be using much, so I won't spend time on it. Any questions, comments? Okay, so what are the other things I wanted to tell? One is the Bochner's theorem. I wanted to just mention that. Again, I will not give the proof. So this range of Fourier transform on the space of measures. Okay, so what is the range of measure? So let me just define as before. So a function, since we have seen this in the case of circle, we will have a similar thing here. Is said to be positive definite if summation cj phi of tj minus tk is greater than equal to 0, where the sum is over j and k from 1 to n. So here I put a conjugate on ck for all n greater than equal to 1, for all points t1 up to tn in R, and for all c1 up to cn in complex numbers. So this is very similar to the definition of positive definiteness that we had on the circle. There, the arguments were on the circle 0 to pi, but here the arguments are on this. So with that, there is a nice characterization, which is Bochner's theorem. So let phi be a function from reals to complex numbers. Then phi is equal to mu hat for some mu in M of R, if and only if two things: phi is continuous and positive definite. Okay, both these are, I mean, continuity is necessary. Fourier transforms of measures are continuous, I have already argued, but it also has to be positive definite. Okay, and that is if and only if condition. This is called Bochner's theorem. I will not prove it. So one way is an exercise. Show that if phi is mu hat, okay, you already know it's continuous, show that it is positive definite. If you go back to the proof in the case of circle, you will get the same proof. Okay, I will not prove it the other way, which is a little involved. I mean, one can do it, but anyway, if you know the theorem, you can always read up the proof sometime. I don't want to spend time on it. Yeah. So that is Bochner's theorem. So this identifies exactly the range of the Fourier transform on measures. There is no analogous theorem for L1 functions. Okay. Okay. What else? Yeah. So L2. What about L2 functions? Can we define? We have defined Fourier transform of L1 functions. How do you define Fourier transform of L2 functions? Here, the real line is more similar to integers than to complex than to circle, because L1 doesn't contain L2, right? So we don't have. So how to define Fourier transform on L2 function? Okay, Fourier transform for L2 functions. So it is just like in Z, L1 of R does not contain L2 of R. But there at least it's kind of the other way. L1 implies L2. But here, now is it true that L1 of R is contained in L2 of R? Neither is true. In integers, L1 was contained in L2. In circles, L1 contains L2. But here in real line, neither is true. Okay, so how to define Fourier transform of L1 function, L2 function? So that is the question. So the idea is similar. First, let me give the broad outline. So basic point. For f in L1 intersection L2, show that f hat is now well defined. Show that f hat is an L2 function and its L2 norm square. Its L2 norm squared is, I think, there will be a factor which may be 2 pi squared. So let me try to figure that out. There is a factor here which will be the L2 norm squared. Okay, so let me just what is that factor? We can try with again. Always we can take Gaussian, for example, e to the minus x square by 2 over square root 2 pi. Then f hat of lambda is e to the minus lambda square by 2, right? So what is L2 norm squared? Will give me 1 by root 2 pi into integral e to the minus x square dx. So that will give, this is variance is 1/2, right? We square it 2 into 1/2. Variance is 1/2, so it will give me, I think, 1 by square root of 2. Is that correct? Yeah, this decays faster. It will be less than 1. It will be 1 by square root of 2. Whereas integral f hat squared d lambda will give me e to the minus lambda square d lambda. Okay, I don't even need to figure out, because this and this, okay, it doesn't matter whether it is 1 by square root 2 or not. In this case, we see that this is not equal to, actually there is a factor of 2 pi, not, because we are squaring it 1 by 2 pi. So you have to take f hat squared will be 2 pi times that. So we get that. So this is just a cross check. This is a cross check to see that this 2 pi factor is correct. Okay. So that is the thing that one must prove. But once you prove that, assuming this, how do you proceed? Again, L1 intersection L2 is dense in L2. And what we are having is Fourier transform is uniformly continuous on L1 intersection L2 with the L2 metric. Not if you put L1 metric. Here this Plancherel is in, this is Plancherel theorem. this is for L2 norms, not L1 norms. So this, if you look at L1 intersection L2, it's the L2 metric, then this shows that it's uniformly continuous because f minus g Fourier transform L2 norm is same as square root 2 pi times f minus g L2 norm. So this is actually uniformly continuous. Hence, extends to in a unique way to an isometry of L2 into itself. And then you show that it is in fact onto. Okay, so that way it is similar to what we did on integers. So you can define for L2 functions, you can define and then you can transfer. Okay. So this is the thing that needs proving. So let me for the moment leave it aside because there are other ways. I mean, maybe I thought I was wondering whether to introduce Hermite functions and so on, which are also nice to know. And then one can do it that way also. So let me for the moment leave this point, assume this point. Okay. So this is how you extend Fourier transforms for L2 functions. So it's not defined directly. You can't define it with the integral formula. Okay. So this definition of Fourier transform is valid only for L1 functions, not for L2 functions. So L2 functions have to be always approached by approximation. So if you want to actually work with L2 functions, you can always take L1 functions which converge to that function in L2 metric. And then for those L1 functions, you can use that formula. Okay, so that's how you approach. And once you do that, and then also you can by Riesz-Thorin, what we can do is, so we know that if f is in L1 intersection L2, then norm f hat infinity is bounded by norm f L1. And norm f hat 2 is same as square root 2 pi times norm f2. Because of these two things, by Riesz-Thorin theorem, you get Fourier transform extends from as a operator from LP to LQ, where 1 is less than P less than 2, or can you of course endpoints, and Q is correspondingly going from infinity to 2. When P is 1, Q is infinity. When P is 2, Q is 2. It goes like that. In fact, they are the conjugate exponents, right? 1 by P plus 1 by Q is 1. And f hat Q will be less than equal to, I think, okay, one has to figure out Cp times norm f P for all f in LP. Okay, so this Cp maybe it's you can put 2 pi, but I think it is actually square root 2 pi to a power. Something like, so it depends on, so if you are at this end, you have the constant is 1. This side you have the constant is root 2 pi. I think you will get a power of that. So what is the power? So some power, which I don't know. If you look up the statement of this theorem, you will get that. Anyway, that's not optimal constant, so that you get. Okay, so this is Hausdorff-Young inequality, it's called, and so on. Okay, so that is about Fourier transforms on L2 and LP functions. So we will not be using much. L2 is important, but okay, sorry, here I made a small mistake. So when I said isometry here, what I mean is in a general sense, I mean in a more general sense that f hat 2 squared will be equal to 2 pi times f squared. As long as that factor you know, it's whether it's isometric, the factor is 1 or 2 pi, it's just a matter of, I mean, it makes no difference. difference. It is like isometry. So Fourier transform divided by 2 pi would be an isometry or something like that. But yeah, so this is the L2 business. Okay. So now, okay, what's happening? I don't know why is this is. Okay. Okay, so that is that. Yeah, how do we? There's another way to do this one. Maybe. So there are two things I wanted to tell. I mean, I said I would finish today, but clearly I have not finished. One thing I want to do is the Poisson summation formula, but maybe I'll leave it next time. So another way to approach this L2 theory, so which is nice. So it introduces some things. So maybe I mention it. Another approach to L2 theory. Okay, so let's start with Gaussian. Okay, so let phi of x be 1 by root 2 pi e to the minus x square by 2. So what we know is that phi hat is equal to square root 2 pi times phi. Okay, this is already an L1 function. So we are only assuming L1 theory. We know that this is the case, right? Now what happens? What do we know about the, we also know two things. So let me just write that here. What is f dash? So if f is in L1, so let me just write without the conditions. You know, you have to write all the conditions. If what is f dash hat of lambda? It is always minus I lambda f hat of lambda. Also, if you take similarly, and if you want f hat dash of lambda, that will be what? Yeah, so if you take x times fx, minus ix fx is the, its Fourier transform is f hat dash of lambda. Is that correct? Have I written it correctly? This. Um, no, right. So what I want to do is the following. So if you look at, so let's look at, so let's consider minus d by dx plus x. Okay, and apply it on a function f. Let's call this g. Assume everything exists. Then what is g hat of lambda? Firstly, you have minus f dash hat of lambda plus you take the function x f x, its Fourier transform evaluated at lambda, right? Now f dash hat of lambda is, as we saw, is minus, is now I lambda f hat of lambda. Okay, and what is x f x? Fourier transform will be, again, if you transfer the I to the other side, you will get plus I times f hat dash of lambda. Okay, so what we get is I times, it's again same as I times d by d lambda plus lambda f hat of lambda. Okay, it is not minus d by d lambda, but it is d by d lambda. Okay, so is that a problem? Or did I make a sign mistake? I'm wondering. F dash hat is minus I lambda, but why do I get here minus ix? This is ix, right? Does anyone see it? Is this ix or minus ix? If I differentiate f hat, where is it? Right, if I differentiate f hat, where is it? Yeah, f hat derivative is, that is minus ix, but What is f dash derivative? So f dash Fourier transform will be, if you differentiate here, you get I lambda. Okay, actually I made a mistake. I think it is I lambda f. Yeah, is this I lambda or minus I lambda? I mean this one. Can anyone see quickly, because that makes a difference. I mean, anyway, I can't complete it, but I want to make the point and then finish. Does someone see what it is actually? Okay, so f dash hat of lambda. Okay, let me do it then. Because I think there is a, I should get back. So I'm making a mistake, I think. So yeah, it is 1 over I lambda. So f dash hat of lambda is, no. What the hell did
I think the first one, if you do integration by parts, maybe you get a negative.
No, that's what I'm doing, but
No,
I
there
got
is
the
no
lambda
1 by lambda in that.
No,
I
there's
think
no 1 by I lambda,
you are
right?
doing,
It's
yeah,
on
first
top,
one has
right?
no 1 by
Minus I lambda.
lambda.
Oh, it's 1 by I lambda. Oh, right.
No, you have an f dash, right?
No,
So
no.
you're doing
The
integration by
integration
parts.
by the integration by parts, you have done both. You can only
Oh, I
use
see. Okay. Sorry, I did some nonsense integration. Okay. First we do the f, right?
Yeah.
Yeah. So it is f of x e to the minus I lambda.
It's
x.
1 o'clock.
And then minus, I do f of x, and then I differentiate this with respect to x. I get minus I lambda. So this becomes plus I lambda. So it is I lambda f hat of lambda, right? So this is plus I lambda. So, okay. So now going back here, that makes it minus I lambda. This is minus I lambda f hat of lambda plus I times f hat dash of lambda. What does that become? You see that point, now it is good because I get, let me pull out minus I out. No, not my, yeah, let me put minus I out. So I get minus I times minus d by d lambda plus lambda times f hat of lambda, right? It's the same operator applied to f hat. So what we know is like Fourier f this. So what is the point of this? I start with this phi, right? I get phi hat, which is a multiple of phi. So this can be thought of as phi is an eigenfunction of Fourier transform with eigenvalue lambda 2 pi. Okay, don't ask me where is the eigenvalue, what is the space we are working with, but Fourier transform of phi is a multiple of phi, so it is formally an eigenvalue. So what we do is now we keep applying this. So keep applying this operator. Okay, so let's call this operator A. A is this operator minus d dx. So if you take A phi hat, what will that give me? It will give me minus I times A applied to phi hat. That's what we are getting, right? But phi hat is just square root 2 pi. So it is minus I and square root 2 pi A times phi. So what this shows is that A phi is also an eigenvalue, also an eigenfunction with eigenvalue minus I times square root of 2 pi. So you can keep continuing like this. You can more generally, you can take a to the p times phi hat. You keep doing this inductively, you will get minus I to the power p. Each time you apply, you get, and then you get a to the p applied to phi hat. But then that will pull out a factor of square root 2 pi, and you will get a to the p phi. So this means a to the p phi p greater than equal to 0 are eigenfunctions of Fourier transform, and the eigenvalue will be always there is a factor of square root 2 pi times minus I raised to the power p. Okay, so I will continue. These are what are called Hermite functions. Okay, so this a power p phi is the Hermite functions, and they give the eigenfunctions of Fourier transform. So next time I'll say how you can build the L2 theory using this. It's but okay, I will maybe stop here. Are there any questions, comments? Was this clear? At least what I said here. This should be completely correct. I mean, there is no gaps in what I said here.